Background-Independence. I've already used this joke on several of you at lunch, but I'll use it again anyway. That this is a sort of S knows that P talk for the let MG be a space-time crowd. So it's a little bit like conceptual analysis of this interesting concept that people use when they talk about quantum gravity, and I think the aim is to sort of provide an explanation. But we can talk. That'll become more clear as we go, I think, what I'm muttering about right now. Let me start muttering about the slides. So I'm going to start by just talking about a little bit of motivation, like get you in the mood for talking about background independence. So here's a little bit of Einstein. He's actually talking, it was written in like 1916 or 1917 or 1918. But he's talking about special relativity. But it'll do just as well if we imagine he's talking about general relativity. So these are some notes he started writing and never finished. Ask an intelligent man who is not a scholar what space and time are, and he will perhaps answer as follows. If we imagine all physical things, all stars, all light taken out of the universe, what then remains is something like a giant vessel without walls called space. With respect to what is happening in the world, it plays the same role as the stage in a theater performance. In this space, in this vessel without walls, there's an eternally, uniformly occurring tick-tock that is time. Most natural scientists up to the present had this conception about the essence of space and time. Okay, so in special relativity, of course, the distinction between space and time gets erased in a certain way. But the rigidity of the stage is still there. In every special relativistic world, space-time has the same structure. So it provides a sort of proscenium arch and so on that's invariant. Every time you go to the theater, you're stuck with the same geometry for the stage. What's amazing about general relativity is that it erases that. The stage itself becomes one of the actors, right? Or that distinction is erased, or something. But work on the metaphor while I'm talking. Okay, and that's clearly like an amazing novel feature of general relativity. And a lot of people feel like general relativity is the good kind of revolution. The kind of revolution that you don't want to roll back afterwards. And so the fact that in general relativity, there's no fixed stage that's invariant across worlds means that in our quest for future physics, we should be looking for theories that have that feature. Okay, just a little more Einstein as a way of warming up. So remember from his canonical presentation of general relativity in 1916, this thought experiment about the globes. So what you're supposed to picture is a world that's empty other than two balls of fluid. And what we can say about the balls of fluid is one is spherical and the other is oblate. It's kind of squashed in one direction. Now, according to the spherical one, and they're also rotating relative to each other. According to the spherical one, this guy is rotating around his axis, and so it sort of makes sense that he's squashed. According to this guy is rotating around his axis. Einstein's point in bringing up this thought experiment is there's something weird about physics as he found it, he thinks. In physics as he found it, there's a fact about which one is right, about who's at rest and who's rotating. And that explains the difference in the shape between the two spheres. And he thinks that's a defect in physics as he found it, that he's hoping to repair in general relativity. In classical mechanics, and no less in the special theory of relativity, there's an inherent epistemological defect. What is the reason for the difference in the two bodies? No answer can be admitted as epistemologically satisfactory unless the reason given is an observable fact of experience. But in special relativity or Newtonian physics, the reason that will be given for the difference between the two bodies is one is rotating relative to the absolute geometry and the other one isn't, because it's not observable, so it's inadmissible as an epistemologically satisfactory explanation. Newtonian mechanics doesn't give a satisfactory answer to this question. It pronounces as follows. The laws of mechanics apply to the space R1, right, relative to which, in respect to which the body S1 is at rest, the spherical one, but not to the space R2, in respect to which the body S2 is at rest. But the privileged space R1 of Galileo, thus introduced, is a merely factitious cause. That's like the weird German, and I think this is like etymologically related to fingo in hypothesis non-fingo. Okay, and not a thing that can be observed. Okay, so this is Einstein thinking about how awesome his new theory is going to be. It's not going to offer these kinds of explanations because the stage isn't going to be fixed from world to world. The stage is going to be different. It's going to depend on the distribution of matter and energy. And so his theory isn't going to suffer from this kind of defect. Okay, and today, just to make sure I keep moving along, I'm just going to take for granted a couple of things. One is that general relativity, so our target is this notion of background independence. Right? That's the feature that general relativity has that the other theories didn't have. I'm just going to take for granted that general relativity is background independent par excellence. Okay, so there are some people who think, oh, general relativity isn't even background independent because blah, blah, blah. I'm just going to set my threshold of background independence so that general relativity clearly clears the threshold. Okay, and also I'm going to take for granted that it's of interest to know which other theories are background independent, which new theories that people write down are background independent, because I'm going to take for granted that it's the thought that the general relativistic revolution shouldn't be rolled back has at least a great deal of plausibility. And so we should be interested in this project of figuring out which theories are background independent and counting in favor of theories if they are background independent and against theories if they're not. Of course, it's not definitive, that reason. It's just something that's natural to be interested in, given our starting point. Okay, so I'm going to present one explication of the notion of background independence. We can talk about other ones in the question period. I'm actually talking about some papers of mine from years ago that I barely remember that I had to reread to prepare the slides. But there's an actual expert in the room, which is James Reed, who's recently written a definitive discussion of the state of play on this question. And so if you want to know more, you should ask James. You can try asking me, and I'll probably try to make James answer questions. Or in some cases, Carlo, who's only here to torment me. This seems to have stopped working. I may have. Maybe I press it. Oh, okay. It moved. Oh, wait a minute. It moved because you moved it?
Because I got up.
Yeah. No, it's. Maybe I can just shout pull every time.
That's me.
How'd you do that?
No, I did that.
You just keep doing that at whatever rate you like, and I'll get through the talk.
I don't know, but yesterday when I did it a couple of times, it made it work again.
Okay, I'm going to leave it there, except when I need it. Maybe that'll help. Okay. But this is the one we already have. Okay. Yeah. So this is one of those clever Beamer things where I've got an outline here that you can't see. So the next section is called examples. Okay, and because it's a kind of S-Notes and P talk, I want to soften you up with a bunch of examples that I think are important and help to clarify what we're up to, which are all obviously chosen to make my final analysis look good, and other analyses look bad. Okay, and then I'll present very quickly my notion of what I think of how we should think about background dependence, and then a somewhat more elaborate discussion of what background independence is, and I believe at the end there's a slide helpfully listing some worries you might have about the whole approach. Okay, so just to keep things simple, I'm going to talk about relativistic field theories. What I have in mind is, to present a relativistic field theory, you give somebody a space-time manifold, so a fixed one, unfortunately. That's just for sort of technical reasons, that's the way we're going to do it. You're allowed to give them some fixed fields on the space-time manifold, like you might give a fixed metric, right? Or something else, fixed frame. There's all kinds of things you might do, or you might not. You don't have to fix anything. Then you write down some dynamical fields, like the things that are going to be governed by the equation, the things that are going to vary from solution to solution. Yeah?
V is just a manifold? Or
it is just a manifold. Just a manifold. Then you're going to write, so these are all the, the sort of varying fields that vary from solution to solution. There's going to be equations that tell you which ones count. Before there's a set of equations, just to make sense of the equations, you've sort of got to say, okay, these are the ones that are up for grabs. Like at this stage that you build in conditions like regularity conditions like differentiability or something like that, or maybe some boundary conditions. So there's a space of kinematically possible field configurations. And then the equations that you write down, cut that down to the ones that represent physical possibilities. And just to keep things simple, there's always going to be, among the fields, well-behaved Lorentz metric. Okay, so that's basically a bookkeeping thing. It makes it so things fit on the slides. Okay, so here's a paragon of background-independence. General relativity in the so-called cosmological sector. Cosmological because it's hard to handle spatially infinite cases if there's a lot of matter. So if you want space to be full of matter, you make it compact, you make it finite. So it's not necessarily that we believe the cosmos is finite in this way, but just to do the mathematics of general relativity applied to cosmological problems, you always end up picking a compact manifold to be space. Okay, so time is like just real numbers, there's some other finite thing that's representing space. The only field in this is the metric field, G, and the equation of motion is just going to be the vacuum Einstein equation. Okay, so that's background independent, right? That's Einstein told us it was. We're going with that. That's background independent. Here's a paragon of background dependence. It's a kind of thing you get in special relativity. And so space-time is R4. There's a fixed field, which is the Minkowski metric, the standard one. There's a dynamical field, which is some scalar field that you're using as a toy model for something. And it obeys the wave equation for that space-time metric. That's background dependence, right? Because whatever's going on physically, space and time, the space-time structure that's calling the shots in the dynamics here is just fixed. It's not varying at all. Literally the same in every solution. Okay, so first idea. Well, maybe background independent means generally covariant or something like that. Right? So that one on the previous slide wasn't generally covariant because we put down a fixed Minkowski metric, so we were privileging certain coordinates. So maybe background independent means generally covariant, no privileged, a priori privileged coordinates. Everything has to be sort of written down in clever tensor ways. Right? It was certainly a difference between the paragon of background independence and the paragon of background independence. But no, it won't work. Right? This is sort of like what Kretschmann pointed out in 1917 to Einstein. Because we could rewrite the theory of the wave equation in Minkowski spacetime so that it is generally covariant. Right? We take the same spacetime manifold, we make both the metric and the scalar field dynamical objects, and then the equations of motion, this one just says the metric's flat. Given our topology, it has to be the Minkowski metric. And then this one says, oh yeah, and the wave equation, the scalar field satisfies the wave equation for that metric. So it's basically the same theory, just rewritten in a clever way. It's generally covariant, but since the original version of the theory was definitely background dependent, we want to say this one is too. Space-time geometry is fixed. It's the same in every solution. Why would we call that background independent? It'd be crazy, so this suggestion has to be wrong. Okay, here's another one. This is sort of 1960s technology. Maybe background independent means free of absolute objects, and background dependent means there are absolute objects. So absolute object is a sort of technical notion introduced by Anderson originally and then elaborated in slightly different ways by Friedman and Herman. Roughly speaking, it's a tensor that's the same in every solution, where the same means either locally or globally, you can find a diffeomorphism that maps how the tensor is in this solution, in this part of spacetime, into this other part of spacetime in another solution that matches up, say, well, that's an isomorphism. So what that means will vary depending on what kind of tensor it is, but the idea is clear enough, right? So in the case of the second version of the scalar field on Minkowski spacetime, the metric field was a dynamical object in the sense that It wasn't fixed from the beginning, but because it had to be flat in every solution, there was really no freedom there. It was an absolute object. It was secretly the same in every solution, even though it wasn't literally identical in the way it was laid down in every solution.
Does this also have to represent geometry in some way, or gravitational field, or can be anything?
Anything would count. Yeah, okay, good. This is a good question. So I should say,
Does any scale of field?
oh,
Like I said,
it can't be quite that crazy. Because, there's the solution where the scale is 0, and there's the solution where it's doing all kinds of crazy stuff, and those won't be the same. But there are other cases, like if I have a non-zero timeline vector field, locally that will always be the same because it was sort of straightening out the vector field theorem. So that will count as an absolute object. Is that problematic? I mean, it sort of depends on whether you think it's obviously supposed to be doing the geometric job or not. But to answer sort of the bigger question lurking in the background here, what I'm thinking is, in these theories that we're writing down, we're interested in thinking of them as being representations of very simple but complete worlds, right? So we're not considering, say, subsystems, because if we're considering, say, subsystems, then it could be that there's sort of like something that looks like background structure, but is really representing external fields, externally prescribed fields. That's not the spirit. We want to think, if there's background structure here, it's probably geometric, is what else would be. Good. Okay, so here's the suggestion. Sorry.
So the story is very different depending on whether we assume that it has also has a global condition or a local condition.
Right, we had two different versions of the.
Easier to find absolute object and just looking for an object, something which has local
We get two different versions of the proposal, and the next slide is supposed to show that neither one of them works.
No. You just press other buttons than these two. You should really only press these two.
But that's so hard to remember. All right, I'm sorry, Chris. Okay, so consider the following equation. It's like very similar to the ones we've had so far, except now space, instead of being R3, is a torus. So we've just compactified space in the most simple-minded possible way. The dynamical fields, just like in the most recent slide version theory we had, are going to be a scalar field and a metric. The equations of motion are again going to say the metric's flat and the scalar field obeys the wave equation with respect to that metric. Now, this is just slightly different from the Minkowski case because, say, absoluteness is a local notion. Right? Then the metric here will come out to be an absolute object. Because locally, it's the same in every solution because we put down this field equation. But there are geometrical degrees of freedom in this theory because we haven't said how big the spatial torus is, right? Or whether all three sides of it are the same length or anything like that. So there's actually lots of different shapes space might have, and we haven't said what they are. So it would seem weird to count this theory as being background dependent in the same sense as the version on Minkowski spacetime, because there's some geometry that's varying from solution to solution. So that takes care of one wing of the dilemma. On the other hand, if absoluteness is a global notion, then this theory doesn't have an absolute object because there's no global diffeomorphism. Between an arbitrary pair of solutions, there isn't a general global diffeomorphism that maps the metric to the metric. But it would be even stranger to classify this as background independent in the same sense as general relativity because an awful lot of geometry is fixed from solution to solution, even if not everything is. So this proposal doesn't quite work. Okay. I'm going to carefully press. It worked. Okay. Incredible. Okay. And here's another example that shows that proposal isn't going to quite work. Consider general relativity with some asymptotic boundary conditions. So, and somehow we're just thinking we're modeling an isolated system that's in an otherwise empty infinite space, not that that there's some other stars beyond the boundary conditions. Okay, so Spacetime is R4. There's a fixed field. This is a sort of clunky way of imposing the boundary conditions that fits on one slide. There are other more intrinsic ways to do it, but let's just stick with the clunky way. So we're going to have a fixed field, which is the standard Minkowski metric. And then our dynamical field that represents the geometry of spacetime intuitively is going to be another metric. And we're going to require that the physical metric look arbitrarily similar to the non-physical background metric if you go out towards spatial infinity far. In fact, there's going to be a fall off, something about the rate as well, but we don't need to worry about that. And the equation of motion is just the vacuum Einstein equation. Okay, so we're basically saying something about how things look at spatial infinity as part of our theory. We've built it in as boundary conditions. It looks like Minkowski spacetime can go far. Okay. So this is a theory basically without absolute objects, but I claim a theory in which there's at least a little bit of background structure because of this feature. So here's Einstein again. He considered theories like this. He says these boundary conditions presuppose a definite choice of a system of reference, which is contrary to the spirit of the relativity principle. A definite choice of system of reference, not in the middle of space-time, but at infinity. So there's a preferred, the way people would put it now is there's a preferred set of Lorentz frames at infinity if you impose these boundary conditions. Okay, that's sounding a little like we're falling short of full background independence because we've got some preferred frames at infinity. A similar sort of thing, I don't believe that these boundary conditions apply in principle. If this were the case, my entire theory would have to be rejected. Okay, so he's in the grip of some mania here about general covariance and general relativity and something. But the underlying point is a theory generally invariant with regard to the differential equations regarding arbitrary solutions, substitutions, but not generally invariant with regard to boundary conditions is a monstrosity. Okay, so he thinks there's a huge difference between a really background independent theory like he thinks general relativity is and a theory in which you select preferred frames in infinity. So it definitely, I mean, his whole point here is this kind of theory is not background independent. I'm going with Einstein on this one. So I'm going to say this is a theory without absolute objects, but which is not fully background independent. Okay, so here's another idea. Okay, it's like playing this game, example and counterexample. You should think, yeah, all right, those ones weren't quite right. But there's going to be something in the neighborhood that sort of does the job. Like we just have to add a few more clauses or something. This is why I told you it was going to be an S knows and P talk, because everybody gets to that stage at some point in the S knows and P talks. Okay. And my claim here is like, not that there's no way you can do it, but that there's no way you can do it by just looking at the mathematics of the relativistic field theories. Okay, so the way I'm presenting these things, just a list of mathematical things. You're never going to get a satisfactory notion of background independence that just looks at those. You have to put in some interpretive goodness. So here's an example that's meant to illustrate that. So now the space-time manifold is spatially a three-sphere. There's, again, a scalar field and a dynamical metric field. There's the equations of motion say the Weyl tensor of the metric vanishes. This funny thing vanishes, and the scalar field satisfies the wave equation. Okay. The point of these two equations is that they force the space-time metric to be a metric of constant curvature. And then the topology and the global conditions we put on the metric force it to be de Sitter metric. So the only solutions for G here look like the de Sitter metric. So I'll talk about this more on Friday, but like basically the de Sitter metric is what you get if you start in a 5-dimensional Minkowski spacetime and restrict attention to a hyperboloid consisting of points that lie at some fixed distance from an arbitrarily chosen origin. Okay, so it's like the sphere for Lorentzian geometry. And like the sphere, like what you get depends on the radius from the origin that you choose. And one way that's reflected is you get different values of the curvature depending on how big you make the sphere. Same thing with the de Sitter thing. So we have it quite fixed, the metric up to diffeomorphism here, because the value that the scalar field, the constant curvature that we're talking about can take varies from solution to solution. That's the point. So it's like I said, pick a sphere, but I haven't said what radius. Now, some of you will be thinking, oh yeah, but who cares? Right? Because there's no like two different possible worlds where space is spherical, but they differ in their radius. That doesn't even make sense to make that comparison across worlds. And others of you will be thinking, well, you know, in this case, like maybe I think space is granular, and there's a preferred Planck scale or something, and then I sort of do feel like it makes sense to compare the size of two different de Sitter universes. Now, depending on which of those two ways you go, you'll arrive at different answers about whether or not this is a fully background-dependent theory. And that shows that formal conditions alone won't settle it. You have to put in some interpretive input. Right? So is this theory as background-independent as its counterpart in Minkowski spacetime? Well, it depends on whether you think that de Sitter spacetimes of different radii are the same geometry or not. And so if you don't, then you should think that this theory is, if you think they're geometrically distinct. Right? So if you don't think they're geometrically distinct, you think there's just one space-time geometry here, then this is like every bit as background-dependent as the scalar field in Minkowski spacetime. But if you do think that you can have de Sitter worlds of different sizes, then you should think the geometry isn't quite fixed, and so it's more like the torus case, so there's a little bit of background independence here, but not much. So the answer you get depends on your interpretive commitments. I'm in theory halfway through, right? Yeah. I mean, in the sense that I've been talking for half an hour, if I'm aiming to talk for an hour. Okay.
You started 5 minutes late.
Okay, so I'll skip this one. We can come back and talk about it if you want. I mean, this is like something with more than one metric where there's a kind of ambiguity in how we interpret the theory. We could choose, there's two metric fields, and depending on which one we think is representing geometry, we get different answers. But we talk about that later. Okay, so here's the upshot of this examples section. First of all, background independence is a matter of degree. So I think these are desiderata that any good account of background independence should be able to capture. It's a matter of degree. So we had those cases where it was like almost like just the scalar field in Minkowski spacetime, but there was a little bit of geometrical freedom, but not too much, like nearly background dependent, but not quite. And then we also had at the other end, general relativity with asymptotic boundary conditions is like almost background independent, but not quite. Right? And that a little difference was enough to like really bother Einstein. Right? So we definitely have matters of degree at either end. We have it's not just a formal matter. Your interpretive commitments about how to count geometries is going to make a difference. That's not so surprising when you think about it. And also asymptotic boundary conditions can lead to a degree of background dependence. So those are three things. And like those proposals we considered at the beginning, like I was sort of giving one counterexample to each, but I mean, with these ideas in mind, you sort of give batches of counterexamples to each. Yeah.
So what are these boundary conditions like? I mean, are you mentioning a theory where you could just lop off the boundary conditions and now you have a more general theory that wasn't background dependent in that way? Or are these boundary conditions appearing because it's sort of a consistency condition on the other parts of the theory that it had this particular background? And in that case, I don't quite get the feel for it. I mean, maybe you want to talk, should ask again later. If it's really just a consistency condition, why is that background dependent? Like, maybe this is coming back to
it's not
interpretive.
It's not really a consistency condition. It's more like, I mean, the actual motivation for imposing boundary conditions is because we want to be able to talk about things like the mass of isolated systems. And absent such boundary conditions, we can't do it. So it's kind of, a third option. Okay, but let's come back to that. I think this is good job. Okay, so background dependence. This is going to be short. I think that's one slide. So just thinking about the case, the de Sitter spacetime case, right? That was meant to drive you to the following, into the following form. So we've seen examples of field theories in which indecision about whether or not two solutions have the same geometry led to indecision about whether the field theory was fully or just nearly background dependent. I skipped one of the two examples, but it would do the same job as the first one. Okay, so it looks like if we're going to define background dependence, we've got to help ourselves to the notion of when two solutions have the same geometry. Okay, and this is something extra on top of the mathematics. So let's make life simple. Let's just add, we've got our relativistic field theory, we've got a space of solutions, we're going to add an equivalence relation that says when two solutions have the same geometry. And then if there's only one equivalence class, that's great, we've got full background dependence. If there's a small number of equivalence classes, then we've almost got background dependence. And if there's a lot of equivalence classes, we don't almost have background dependence. Nice and easy. Okay. Background independence is going to be a little more complicated. So here's the clue that we have. The hallmark of background dependence is that solutions representing physically distinct histories correspond to the same geometry. So there's no dependence of geometry on physical degrees of freedom. And the thing that makes this project tricky is trying to capture the role that asymptotic boundary conditions can play. Otherwise, it would be easier. So we're after a sense in which asymptotic boundary conditions constitute background structure and general relativity. So we'd like to find a sense in which, in the presence of asymptotic boundary conditions, there's less thoroughgoing dependence of geometry on physical history than there is in the absence of the boundary conditions. And so in general relativity, in the cosmological sector where everything goes nice, just exactly like Einstein would like, there's like complete dependence of the geometry on the physical degrees of freedom. The field, I mean, because the metric field is the physical degrees of freedom. There's nothing else there. Somehow that misfires slightly in the case of asymptotic boundary conditions. So what we're looking for is a sense in which, in the presence of asymptotic boundary conditions, it makes sense to think of two solutions with the same geometry as being physically distinct, so that there's not quite perfect dependence of geometry on physical degrees of freedom. This is just foreshadowing. It doesn't matter whether it may not seem to be transparent right now what I'm aiming for here, but I think it'll become clear as we go. Okay, so subsection about gauge equivalence, and then another subsection that even I can't read, even though I, in theory, know what it is. Just warning you that this section is going to go on for a little while compared to the previous. So this is going to be getting together the tools to make out the sense in which the asymptotic boundary conditions lead to a theory that's almost, but not quite, background. Okay, so let's think about the spatially compact case in general theory, where everything works out just as we would like. So here we think everybody will have been brought up to think of solutions of Einstein's field equations that are related by diffeomorphisms as being incapable of representing distinct physical situations. That's you will find every authority writing a textbook about general relativity at some point saying something about this. Warning you, don't think of diffeomorphically related things as corresponding to distinct possibilities. Why? Well, the whole argument. So let's set it up like this. So say we've got a solution, so spacetime manifold plus a metric. And let's say we've got a diffeomorphism from the metric, from the spacetime to itself. That's a whole diffeomorphism in the sense that here's our spacetime. Here's some Cauchy surface relative to the metric. Let's say that we've got a diffeomorphism that leaves an open set containing that Cauchy surface invariant and messes around with things elsewhere. Okay, so maybe just to the future. Okay, so I started out with a solution v comma g, and now I act on it by this diffeomorphism, and I get a new solution v comma d star g, right? Which is d is just doing the job of permuting the geometric roles played by the points. It's leaving them literally the same back here, but swishing them around a little bit up here. Right? So maybe there's one point of maximum curvature. According to this solution, it's that point in the background spacetime. According to this solution, it's say that. This point plays the same role in this solution that this point plays in this solution. The two solutions, though, represent the same overall geometry. Okay, so let's say we have a diffeomorphism like that. and consider our second solution here. Now, so now we've got the two solutions. And now we're asking a question about physical situations. Right? It's a question about determinism, so it's not a question just about solutions, it's about physical situations. Are there physical situations S and S star that stand to one another as these two solutions stand to one another? Namely, same overall geometry, but with the geometric rules differently distributed. We always say no. Right? Why do we always say no? Because if we said yes, that there was S and S star that differed from one another in this way, then we'd have to say general relativity was radically indeterministic. Right? For every way the world could be, there's another way the world could be that starts out exactly the same and then departs from it. And that's like a silly way to think of the theory. Why? Well, for one thing, there are actually interesting senses in which general relativity is indeterministic. Namely, there are some globally hyperbolic spacetimes that have non-isometric extensions. So there's different ways the story could be continued that are geometrically different. That's real indeterminism. It would be totally hidden if we let this kind of silly indeterminism. And similarly, the fact that those kinds of counterexamples are really rare and basically the theory really is deterministic would also be hidden if we thought about it this way, so we don't. It would just be pointlessly confusing to say that there were S and S star that differed from one another as these two. Okay, good. So what's the whole argument? I mean, people often go straight from, well, the whole argument, so any two isometric solutions of the field equations have to represent, are incapable of representing different solutions. But that is a little quick if you think about it. The whole argument only sort of can show that if you've got a diffeomorphism that threatens determinism, then you better not count it as generating new possibilities, but it will show that every diffeomorphism has that feature. And now we're going to sort of try to exploit that little tiny gap in order to get the account of background-independence as well. So here's a technical notion, gauge equivalence. Okay, so that phrase is used in a million different ways. This is a stipulation of mine that matches up well with some of the dominant ways in which it's used, and doubtless depart from its moments. Okay, so say we've got a relativistic field theory, and we've got we've set things up. This is a slightly squishy point in the talk. It's kind of,
Can you just move the board like 2 feet to the right?
Yes.
And point it a little bit in this direction. Because then it'll be under that light, I think. And this pen may be a bit shorter. My right.
Sorry.
Come on. And
How's it do?
a little bit further. So then we get that light on it, and people can see it a little bit. Great. So,
Okay, good. Okay, so basically, like what we want is we want to identify those things that are threatening to ruin determinism. Right? So I'm just going to assume we've set up our theory in such a way, like is always either the case of general relativity and Yang-Mills theory and every other theory you can think of, so that there's a notion of isomorphism of solutions, and if solutions are isomorphic, then they have the same representational capacities. In the sense that they can represent, if this solution can represent a given situation, then so can any solution isomorphic. Just assume we've done that somehow. Okay. And we're going to call such an isomorphism a spoiler if it acts as the identity on an open set containing a Cauchy surface. So this is like the whole diffeomorphism thing. That's going to be a spoiler, but this is just slightly generalizing the notion. And then we're going to call two solutions gauge equivalent if there's a chain of solutions that interpolates between them such that each guy in the chain is gauge equivalent to his predecessor in the chain. So the notion of gauge equivalence is the transitive closure of being related by a spoiler. Okay. So this is allowing us to say, okay, we know we've got to count some things as like not capable of representing distinct possibilities because we don't want there to be indeterminism. This is sort of the minimal way of identifying those guys without putting in anybody else by accident that we didn't need to.
This is a refined version of Dirac definition.
Yes. Yeah, right. It's just, I mean, it's it's a very simple surrogate for the kind of thing you find in Dirac or the kind of thing you get in the whole covariant phase space technology. They both lead to, in central cases of interest, this will get that stuff right. But yeah, it's easy to state.
It's also tricky because it assumes that we have a Cauchy surface in the space-time. So
That's right. That's why at the beginning I said for bookkeeping purposes we were going to always require that our relativistic field theories involved at least one globally hyperbolic Lorentz metric.
that's fair, but in case that which is Heisenberg solutions, you don't get out the
No, right. No, yeah. So yes. So there are fancier things we can do in the absence of Cauchy surfaces, but so this is an aside. So think about the kind of thing we were talking about the other day about the initial boundary problem for anti-de Sitter spacetimes. Yeah. So then, there are things that aren't Cauchy surfaces but intersect infinity in a good way, and you can use those as okay. Okay, so what happens in general relativity if you apply this notion of gauge equivalence? Well, you get just what you want. In the spatially compact case, two solutions are gauge equivalent if and only if they're related by diffeomorphism. Because basically, if you've got any kind of weirdo diffeomorphism, you just factor it into two parts, one that leaves the stuff back here invariant and one that doesn't. Okay. And so two solutions are gauge equivalent if and only if related by diffeomorphism, just like you were told in your general relativity test. But in the presence of asymptotic boundary conditions, you typically find that gauge equivalence is a more discerning relation than isometry. So there will be solutions that correspond to the same space-time geometry, but which are not gauge equivalent. I'll say more about this in a second, about how it works for the particular boundary conditions we're talking about. Let me just, as a way of playing defense, say, maybe somewhere in the room now, somebody is frantically leaping through the wall for the killer passage that says this is wrong. And what you'll find is, if you look early on, he definitely says, oh yeah, in general relativity, gauge-related solutions, diffeomorphically related solutions are gauge equivalent, or something to that effect. But then if you look at the final footnote on the second last page, he's finally talking, worrying about asymptotic boundary conditions, and there he says some things that clearly are sort of implying he's, in those contexts, he's going to use this more discerning notion of gauge equivalence. And this is sort of very typical. Of course, pedagogically, you emphasize this case, but then if you've got a fuss with boundary conditions, you move into this case and you come up with this more discerning equivalence relation. Okay, so how does it work in the asymptotically final spatial infinity case? Well, recall that our boundary conditions require the physical metric to rapidly approach the flat, unphysical background metric as you proceed up to spatial infinity. So, any diffeomorphism that sort of doesn't mess around with the unphysical background too much as you go to spatial infinity will preserve the boundary conditions. So you'll have, for any given solution that satisfies the boundary conditions, you'll have lots of other ones that are isometric to it and related to it by diffeomorphisms. Now, it turns out that those diffeomorphisms will count as relating gauge equivalent solutions, if and only if they act as the identity at spatial infinity. So we have to sort of worry about. That's obviously one way to cook up spoilers in this context, right? So pick a diffeomorphism that does nothing up here, back here, and then up here it just messes around with things a little bit, say a compact set, and leaves the boundary conditions to it. Okay, that would be a spoiler, and then two things related like that will have to be gauge equivalent. What you can't do is allow the thing to act non-zero everywhere and expect it to be a spoiler. The spoilers have to leave some Cauchy surface invariant. And it turns out basically what goes on in this case is if you've got a diffeomorphism that preserves the boundary conditions, it can be factored into two parts. A diffeomorphism that acts as the identity at spatial infinity, does less and less as you go out, and a part that acts as a Poincare transformation on the unphysical background. So if you've got something that leaves a neighborhood of a Cauchy surface invariant, it has to be, its Poincare part has to just be the identity. And so it has to be entirely eaten up by the guy that is asymptotic to the identity. So that's why gauge equivalence here is this stronger relation, right? So there will be solutions that are isometric, same space-time geometry, but not gauge equivalent, because they'll be related to each other by, say, time translations at infinity. Okay, good. Final thing I shouldn't leave out. For any solution, the set of solutions geometrically equivalent to G will give you a big equivalence class. And if you then look at the relation of gauge equivalence restricted to that big equivalence class, you'll get a 10-parameter family of equivalence classes corresponding to 10-parameter Y, because the Poincare group is 10-dimensional. So if you factor out by gauge equivalence, then you get a space of like solutions modulo gauge equivalence on which the Poincare group acts. And it has all the nice features you want. It's a symplectic space. The action of the Poincare group gives you conserved quantities, everything you want. So that's why that's sort of the underlying motivation for the interest of this particular notion of gauge equivalence in the presence of asymptotic boundary conditions. Okay, so these are the kinds of slides that John was showing yesterday, just like total toy things. Picture infinite sheet of graph paper. As you go out to infinity, you have to draw the lines asymptotic to, and I'm terrible at doing that, so they don't really look that way yet.
So just in the previous slide, I mean, you don't get sort of conformal transformations in there as well, because we've already decided that those don't give you a semiphysical solution.
Which kind of conformal ones do you mean?
So just multiply by a conformal factor in a whole or something like that.
Yeah, right, good. So,
it's part of our interpretation.
Right.
Physically.
So, good. So, the thing, if you want to put those in, you've got to go back to where I said the definition of a spoiler involved the notion of an isomorphism, and you could go back and change the notion of an isomorphism from our standard one to that one, and then you get different answers. Okay, so toy models, right? So imagine when I pick a color, I'm like telling you about the geometry of space, right? So the idea is like, here's a sequence of 4 different geometries of space. This is like a different space-time geometry that's got a different sequence of colors. Okay. Here we're like, it's the same geometry, same sequence of colors. Right? So these are like supposed to be corresponding to isometric solutions. We're not saying they're gauge equivalent. Okay. In order to be gauge equivalent, it has to be the same sequence of colors in the same order, and they have to if I've got a light blue line over here and a light blue line over here, they have to be asymptotic to the same regions in the background, the unphysical background. That's what gauge equivalence is doing for you in the presence of these boundary conditions. Right, so these are all gauge equivalent. You can do all kinds of crazy stuff in the middle, but as you go out to infinity, they're asymptotic to the same regions. Okay, and once you've got that, you can talk about shifts at infinity or rotations at infinity and so on. Right? So, like that, as we move through this family, it's the same sequence of colors, not asymptotic to the same things, but the ones this family is asymptotic to are shifted versions of the ones this family is. So now we can make sense of the idea that we have 2 different solutions, same geometry, different class shifted. And that's going to lead to the notion of energy, mass, for isolated systems in general. Okay, so here's the proposal. The theory is fully background independent if each class of geometrically equivalent solutions corresponds to a single gauge equivalence class. So this is the case we have in general relativity. Spatially compact general relativity. And it's almost background independent if each class of geometrically equivalent solutions corresponds to a small, for instance, say, finite dimensional family of gauge equivalence classes. Right, so here we have here we have gauge equivalence and geometrical equivalence being the same thing, and we're happy to say full background independence. Here, they're not quite the same thing. There's just a little bit of slippage. It's possible for two things to be the same geometry, but physically distinct in a sense, and we're like, okay, well, that's not quite background independent. And then the definition we had before, background dependence and almost background dependence, basically just counting how many geometrical equivalence classes there are. Okay, so definitions are horrible to look at. So here's like the underlying idea. Background dependence means no dependence of geometry on physical degrees of freedom. Background independence means thoroughgoing, complete dependence of geometry on physical degrees of freedom. Distinct histories correspond to distinct geometries. And in between, you can fall just short of those things, or you could be like really in the sort of no man's land in between. And one virtue of that claim is that it captures this idea that one way to impose background structure is not to put in, not via putting in more fields or like worrying about what you're varying in the Lagrangian and what you're not or anything, but by imposing boundary conditions. Okay, warning. You know, it's tempting to sort of like, and I probably have already accidentally done it, sort of make it sound like if you want to determine how background dependent you are or how background independent you are, you should be counting the dimensions of these families, but it doesn't quite work. I mean, I think informally what you'd like to do is like something more like proportions. You know, how big is the family of gauge equivalence classes in the whole family, in the whole spatial solution? But of course, it doesn't really make any sense. But why do I say that? Well, there are cases where you can impose some background structure and get a certain kind of asymptotic symmetry group. So that's sort of counting how many gauge equivalence classes there are per geometry. Then you impose some more background structure and you get a way bigger group. And then you impose some more background structure and you get a way smaller group. So imposing more background structure, sometimes it enlarges the size of the asymptotic symmetry group and sometimes it shrinks it. There's a sort of explanation here at the bottom of why that would be if you're interested. The main point of the warning is you can't just count, sadly. Okay, so I think that leads me to my final slide, which is a list of worries I think any reasonable person would have about all this. There are other ones too that I have listed, like should we really be that worried about background independence? I think I'm done. Thanks.
This is just a general point. I'm very interested in the general covariant and variant features of theory. And as far as I understand, any theory can be formulated in a general covariant way, but not any theory is generally invariant. And well, the invariance is usually defined in terms of the invariance of the absolute structure. That you mentioned when you talk about background dependence. So do you think there may be a relation between background dependence and the group of variance theory?
Yeah, right. So, I mean, there's something kind of, I think basically it doesn't quite work. I think it's partly because I'm so hung up on the asymptotic boundary conditions, which that approach is blind to. It just can't pick up on that kind of structure. But also because of the kind of thing I was saying about how you're not going to get it right if you just look at these technical features, because it won't tell you things like, yeah, but when do two metrics really correspond to the same geometry? So like those kinds of examples where, like the de Sitter space example that I gave, that kind of technique just can't give you a final answer because it just works with the mathematics. And another kind of thing in the same flavor would be, theories where you have more than one metric, and you've got to sort of you've got to make a choice and say which one you consider to be the physical metric. The sort of Anderson technique can't do that for you. Yeah.
Can you put a slide in which you give your definition of background?
Yeah.
It went very fast.
Yeah.
This is enormously clarifying to me. To run all this, you need to know what you mean by geometry. Geometry, in a sense. It's very, you have to identify which part of the thing you're talking about is a geometry. Is that right?
Yeah, I mean, I think
is needed. For that.
I think that's right. I think for each of those definitions requires that input.
Core intuitive thing you're saying is that if I really want to go to the core of what people mean by the background independence, geometry is dynamical. In a simplified cutting over.
Yeah, right. So that's
somehow the.
Yeah. So I think that is right. I mean, I think that's I think if you quizzed Einstein about the stage metaphor and everything, I mean, that's what you would have gone. But there's a slight.
No.
I mean, there are like around the edges. There's a little bit of extra. Yeah. Yeah, right. And I think like if you just like in the you can impose the boundary conditions in relativity, you're not going to change the fact the metric is still going to be dynamical. And so like the sort of epicycles I'm adding to that basic intuition is meant to pick up like a few extra wrinkles like that.
But there is another, where I wanted to go is, there's another case in which what you mean by metric is, what you mean by geometry is sort of, apart from infinity, if I work in a thing that defines the term, if I do a quantum theory and I define interpretatively, including for the gravitational field, then I have somehow the notion of geometry split in two parts. One part I use it when I fix the sort of the causal structure of which governs the field algebra, which is given by the background metric. But then I'm saying that if I measure the metric, I'm not measuring the background metric, I'm measuring the fluctuations of the mean. So there, I'm not sure anymore what do I know when I say geometry.
Yeah, I'm not sure either. I mean, I think that's a really interesting case where you're pushing the classical notions pretty hard, and you can't be sure that you're still in bounds. But I think in that kind of thing is not necessarily a weakness. I think I think that kind of approach you really it's hard. There's good reason why it's hard to understand. I mean, there's a sort of deep question about what's going on there.
So you wouldn't know how to apply this definition directly.
No. I mean, I think, so maybe this actually would be bad. I don't know whether. So if somebody just says like, no, let's just count the Minkowski, the H part, as always being the geometry, and the rest is some physical field that we're not thinking of as geometric, but as just. The thing that makes the gravitons that we were expecting to see or something.
That would be definitely non-background.
That would be definitely non-background independent, but there'd be other ways of thinking of it where the geometric structure really is supposed to sort of combine both things.
There's also a kind of symmetry there. You take a different background, split up.
Yeah.
Sort of split the background and the graviton contribution arbitrarily.
Right. I mean, I think that would be a reason not to go, like pick a Minkowski metric and stick with it. I think that would be a kind of crazy reading of the theory, and it would make it come out background dependent. And I mean, it's probably true. There's a lot of theories where if you give them crazy readings, you'll get nice sharp answers, but they won't really mean anything. I think that's probably the right way to think of it. Sorry.
I was wondering if you could say something about the Belot at the end.
Yeah.
Especially What happens if that is included in there?
Yeah. Let me say something about the matter case, and then because I'm hoping to make other people answer the string theory case. Okay. So the matter case, yeah. I mean,
happily we now have an expert.
yeah. That's right. Yeah, so it doesn't always work as well as I would like when there's matter. So I think a way of, I'll explain in a minute why, but let me just say, one thing you could say if you wanted to defend this, even though it doesn't always work that well, is, the really important case is, you want to get right the ones that are just supposed to be about geometry. If you can do that, it's kind of okay. If things go wrong when you put in the matter, well, at least if you know if you took the matter away, it would be background independent. So that's still the joint theories come have background. That's one thing you can say. Second thing you could say is, ultimately, probably, it would be weird to think that there was one right answer to what the definition of background independence is. It's kind of a technical notion that's just been introduced. People obviously use it in different ways. So this is one that works pretty well for some purposes, and maybe there's other ones that are complementary to it. And if you're asking whether a theory is background independent, it makes sense to pick the ones that look like they're sensible for the kind of theory you're talking about and see how they work. Okay, that's my defense. Here's the prosecution. So in order to be fully background independent, you have to have thoroughgoing dependence of the geometry on the matter. So any change you make in the matter has to lead to new geometry. That's, I misstated that. It has to have thoroughgoing dependence of the geometry on the physical degrees of freedom. Any change you make in the physical degrees of freedom has to lead to a different geometry. That's sort of easy when the field that's giving you the geometry encodes all the physical degrees of freedom, like in the vacuum GR case that we were talking about. It can still happen even when there is matter. So if I give you a solution of the Einstein dust equations, I just give you the metric, you can reconstruct the dust trajectories and the matter density in a unique way, just because you just look at eigenvalues of some curvature tensor, eigenvectors of some curvature tensor. So that's a kind of nice case for me, where you still get absolute background independence by the letter of the law. There are cases that don't work quite as well. So in the 1960s, people were interested in this geometric dynamics idea that maybe the metric was everything and didn't need any matter fields. Garros showed that for the Einstein-Maxwell equations, it almost works. But there's a family of null electromagnetic fields for which it fails. You can't, if I just give you the metric tensor so you make a solution of the Einstein-Maxwell equations, I'd give you just the metric tensor. Can you reconstruct the Maxwell field? Almost always, but not quite always. So there's a case where things go a little bit wrong, according to me, because we don't quite get full background independence. But when you spell out the sense in which it falls short, it's clear it's a kind of minor sense, in the same way that the way in which general relativity is genuinely indeterministic is interesting, but kind of minor, just around the edges. So I think, I think that probably the best way to apply these definitions isn't just look at the final answer, but if it falls short of one of the official things, explain why, try to prise apart exactly how it's falling short and how common that problem is. But those are the only two cases, dust and Einstein-Maxwell, that I thought about. I'm not sure how it goes in other cases.
So you mentioned.
Sorry, I didn't talk about string theory, but let me take a couple more questions and come back.
You mentioned in passing there's a sense in which this is an interesting. It's at the very least consider this final conversation. This is a worthwhile discussion on the subject of new theories, say on gravity, to what extent it satisfies whatever formal definition we're going to offer for background. Besides mere curiosity about classifying these different new theories, can you say more about, or more of a discussion argument for why that should be a motivating consideration or desiderata in these two commentaries?
Oh, why it should, okay, I see. So not, I mean, I was talking with Alyssa about this last night, and correct me if I get this wrong. She was saying there are basically like two main streams of justification in the literature for why it's important to have background-independent theories.
That I found, I haven't read it.
You're my oracle on this question. On the one hand, there's a kind of like, okay, we want a theory of everything that's got to include gravitation. We know gravitation should be given a background-independent theory, so the theory of everything should be background. That's one way you could go. A slightly different way is something like the careful study of general relativity, like, you know, it makes you realize it's like a physical insight that theory should. The fact that that theory is background independent isn't just like some nice trick or something. It's one of the central physical insights that Einstein had. And so, you know, it could turn out that Einstein was wrong about all that, but right now we're betting on him having been right about it.
So I thought maybe this is a strengthening point that I was taking, but it's not only that we seem to have failed to locate, especially in formalized singular piece of the theory that is its background independence, but that you can't cash it out in such specific terms. And if that's the case, how can we ever know that? You know, what does it mean for the evidence that led us to be endorsing general relativity endorses this interpretive feature of the theory?
Oh, okay. Sorry. Yeah. Could you say that again? I'm not sure I got it.
So, if you can't, if it is the case that you can't cash out the aspect of the theory itself that that renders that theory background independent, then in what sense can we take away from general relativity that our next theory also has to have this feature?
I see.
Because
Okay.
the evidence can't affix to it if it's not a part of the theory.
So I'm thinking, like, this is one sort of proposal for cashing out what that feature is, and there are other ones, and somebody who wanted to follow this track probably has in mind something, you know, some variant on one of these things, and that's their attempt to cash it out.
Can I give a historical analogy which
Please.
might help clarify the way I view this? I fully agree with what you said in your general presentation of Asian background independence as the feeling that there is some insight obtained in the theory, and in a somehow anti-Kuhnian way, we do believe that insights remain. Now, your question is whether if we can't even say what is the insight. Now, there's a good example of a similar thing, is the Copernican revolution. Nobody ever denied that it was a key insight that Copernicus, and then when it became clear that he was right, was acquired. What is the insight exactly? Oh, well, the sun is the center of the universe, not the earth. That's wrong. It's a misreading of the insight, but the insight is there nevertheless. So let's formulate it in a slightly different way. Well, it's not the earth is not the center of the universe. Okay, it sounds similar in rephrasing, but the second is right, and the first was totally completely wrong. So I don't think there is a contradiction between the existing of a feeling in the physics community that, okay, we have understood something crucial, and the precise characterization not being clear from this crucial. Another example is Galilean relativity. whether there's a tube to Galileo doesn't matter, but also it is a relational relativity. It's true, it's remained to be true in special relativity, in general relativity, but in a slightly different sense. So if you give us the simple characterization, Galilean characterization of velocity being relational, then if you do it wrongly, then you cross away to special relativity. So I think it's a general.
Yeah. I mean, I totally agree with that. Sorry.
I've actually had this very similar line of thought. Sort of one thing that was clear role taking this thing down was that it's something people thought kind of in favor of the theory, and whether there's some sort of nice story you could tell from the formal explanation you gave of why this might be an attractive feature for a theory to have. And one thing I was thinking is this sort of bigger metaphysics hat on, but that when you have this sort of dependence, it might be indicative that there's sort of less fundamental structure in the theory, because maybe sort of some you used to have sort of two different moving pieces of ideology, and now it turns out that sort of covariation is indicative that there's less, and then you might think, and sort of you can use like parsimony and considerations to explain why people thought this was a good thing to have.
Yeah, that's an interesting suggestion. I don't know. I mean, there's another possibility in the neighborhood, which is that one of the things you're doing is sort of moving. I mean, in a way, what you're doing is reducing in a sense, the amount of structure is very vague. Okay, that the nomologically possible worlds share with each other, and that somehow that's a virtue. Although it's a little hard. I mean, when you put it that way, it doesn't sound like obviously good or obviously bad. There's probably something particular about geometry that people feel like, I mean, that's what's special about the general relativities. We learned about geometry that was the kind of thing that should be shared across possible worlds, to the extent that it wasn't all theories. But what makes geometry special? I mean, I think this is like one of the really central philosophical questions that I have trouble getting anybody excited about, because I have so much trouble like even expressing what I feel like the mystery is there. But I think to me this problem has that feature. There's something very special about geometry and the role it plays in our ways of thinking about the world. And you sort of see like there's a lot of strands of philosophy that give answers to that kind of worry about the sort of neo-Kantian things, but I don't feel like any of them really get to the heart of the matter. But I know that I don't get to the heart of the matter. I think for people who are interested in both metaphysics and physics, this kind of question about what makes geometry special, or what makes something geometrical structure rather than some other kind of structure, is like a really, really hard and interesting problem. Sorry, I'll listen. Okay.
Yes. As I take your message here is that you cannot just only look at the mathematical formulas to decide whether it's background independent. You also have to have some kind of physical interpretation judging when two different mathematical representations are the same physical situation. Mm-hmm. And then, so that's just kind of rephrasing what you said. But judgments on whether something is background dependent or independent or not, if your account is right that the physical interpretation is needed for that, I think that the problem when there are these kind of controversies between people, whether for instance string theory is background independent or not, can be sometimes due to the fact that it is unclear part of these issues, like when we take certain things to be the same,
right?
Or also when we commit ourselves to giving a physical interpretation to something mathematical that might suggest a difference when it doesn't. And of course, I don't really know about this, whether string theory is background independent or not, but I think that these kind of issues that you raise would be very important to kind of make more sense of those questions.
Yeah, right. So I think, I mean, it's sort of like the autobiographical background of working on this project was, about, 10 years ago probably. There was like in the popular press even, like this squabbling about whether string theory is background independent or not, acrimonious op-ed articles in the New York Times or something. And when I read some of the surrounding stuff about what the protagonist took background dependence or independence to be, sometimes it seemed to me like it didn't make sense, or sometimes it seemed like it wasn't. It was too special to a particular theory or something. So I was thinking this is the kind of thing philosophers can do. They're good at coming up with simple-minded definitions and counterexamples to them. And, I think a virtue of doing that kind of thing is it potentially clarifies where the disagreements really lie between the protagonists. It's kind of what's Locke's phrase, he wants to be the under-laborer for the Newtonians. Just go out there and clear some brush so that the real work can get done by the real people. It's definitely that kind of thing. If there's a contribution that consists in getting people to agree, we're disagreeing about this because we're disagreeing about what geometry is in this setting, then that is kind of a little bit of light. I haven't forgotten about the string theory thing, but you asked your question, then I'll try to get Nick to talk about the string theory.
Okay, it was just about the quotes you read from Einstein about this boundary, the boundary conditions creating a problem for background independence. Isn't that clear that that's really what he's worried about there?
But that's early, right? That's early.
Yeah, no, that's right. It's
I swear I haven't been messing with it, Nick.
Sure. Way back at the beginning. Just keep going, and I'll tell you when to stop.
There are a lot of things you can be concerned about with that. You're being ad hoc, and it's just it's not clear that that's.
Yeah.
I'm not trying to detect the framework you give at the end is really nice and everything. It's just.
It was still thinking that there were no vacuum solutions.
So let's see. There was Schwarzschild. There was Minkowski. There was Reisner Nordstrom. So it was a crazy. It's at the time Einstein was thinking, and Hilbert as well, that there might only be one non-singular vacuum solution, which is very. This is something about the intuition of very brilliant people. They're sometimes very wrong. In this case, you can't. It's how Hilbert. Hilbert's it's a generalization of Maxwell's equations, and it has no vacuum solutions. It's hard to imagine what he was thinking, but I think he must have been Einstein and Weil were telling him here's how the physics work. It's totally more different than you would expect. Okay. So these particular quotes, so this is from the Cosmological Considerations, so his paper about cosmology from 1917, and at this time, he's running together a bunch of things under the name the relativity principle, including general covariance and what he, by the next year, was calling Mach's principle. But here, it's general covariance that he's thinking of, I think. He thinks no, you're picking special frames. That's inconsistent with how I want to understand relativity. Relativity shouldn't have any special frames. And then he changes that the next year. He's there can be special frames if the matter picks them out. But you can't have special frames that are sort of there from solution to solution independently of what the matter's doing. So that's this one. And this one, this letter to me, I always say this and forget how funny it sounds. It's a guy he's corresponding with who's actually, the letters are amazing because me is always asking the questions that philosophers would like to ask Einstein, and unfortunately Einstein doesn't really like him, so he's not that keen on answering the questions, but occasionally he gives an answer.
I was wondering why it looked like he really worked up.
Yeah, so it's because they've been going back and forth, and me keeps saying this thing that's driving Einstein crazy. He's very, very emphatic about this. Here he's certainly, during this period where he's talking about adding asymptotic flatness as a boundary condition. So let me start again. At the beginning of this paper, the very first paragraph, the very first thing he says is, if space is infinite, we have to add boundary conditions. The obvious boundary conditions are these asymptotic flatness and spatial infinity, but those are no good because they violate the relativity principle. So we have to get rid of boundary conditions by making space be finite, so there's no spatial infinity. And here he's covering the same territory again, and he's like, yeah, the theory, it would be horrible to add the boundary condition. It would just totally ruin the theory. It would change its character entirely. So to me, like, yeah, I think it's the same. The correspondence has been following on from this discussion, and he's expanding here on the sort of thing he had in mind there.
Because he's still thinking it would be covariant.
Yeah. Yeah. He also thinks it would violate Mach's principle, but that's a different kind of thing. But yeah, he's very, very emphatic about this. It's interesting.
A comment about that in Einstein's presentation, I think it's related to the entire story. Einstein oscillated wildly about the interpretation of his theory. And that's, in fact, simplifying enormously, we went to one extreme to the other. One extreme, which is, I think, the motivation of this, is at some point he had the idea that geometry is determined by matter. Yeah. So there's no sense of geometry in non-determinate by matter. And he was resisting the idea that he later abandoned that on the ground that was usually anything else, and moved to the opposite point of view, which is very clear, for instance, in the fifth appendix that he wrote very late to his meaning of relativity book, which is a wonderful text, which I think clarifies enormously this issue, where he not only completely gave up the idea that geometry is determined by matter, but much worse than that, he insists on the idea that geometry is a field which a dynamics and an independent entity by itself, and should be seen autonomously as an entity, dynamical entity, and that which is a gravitational field, and if you take away the gravitational field, what remains is nothing. That's where he has this strong. So I think if he was present of a debate on what's the meaning of background-independence, I don't think he used this expression, he would have oscillated on that and got at the end toward something much, much closer to, if I could say, you mentioned a concern in philosophy about what's geometry. There's a story in relativity, which is geometry is nothing. It's not something primary, it's not something fundamental, it's just one of the fields and the features of one of the fields which are around, and there's nothing that fields that's finalized and in the fields.
I agree, but I'm trying to resist saying anything about it, because are we almost at the end? If I'm going to talk about string theory, should I do it right now?
Yes, please.
Okay, I don't have much to say about string theory, but I want to. So I think, like, look, if you take just like the most naive and flat-footed way of talking about a single classical string propagating, right, the sort of thing that would be at the beginning of the textbook, the part I can understand, it's going to come out to be background dependent, right? Because we're going to have lots of strings, lots of ways a string could propagate in the same fixed background spacetime. So definitely background dependent according to this, if the geometry is latching on to the target space. Okay. Slightly less naive thing you might do is say, like, no, it should really, the geometry that we're talking about should really live on the world sheet. Right? And now, depending on how you decide to individuate geometries, you could probably make it come out to be background independent if you want. A less naive and more interesting thing is to do what Nick says we should do about this kind of thing.
You mean along the lines that Carlo was talking about, sort of before, where you think of the...
Yeah, right, where you think of so basically let me try and then correct me. Okay. Okay, so you think like, okay, in the original flat-footed version where we had the string propagating in fixed space-time background, we didn't really mean that that was a good picture of reality, right? There's something like, okay, this is a sort of semi-classical story, and really that metric, a solution of Einstein's field equation sort of corresponds to a coherent state or something of a quantized string theory. And so thinking about it that way, okay, we are getting dependence of geometry on the physical degrees of freedom, so it comes out as being background independent. I think it's good. It should look different under these different readings. As you get more sophisticated, it's good that it becomes more background independent because that's the nature of the dialectic.
And I thought that was kind of what you were saying earlier. I mean, in that latter picture, it's as if you're sort of the definitions that depend on kind of geometric considerations. It's not sort of how to apply them, but what counts as the geometry is coming from a coherent state of gravitons, and they're dynamical, they're surely dynamical parts of the theory. So you kind of shifted the discussion, but it seems to have the right dynamic character that you wanted. And maybe just another little comment on that, to think about the discussion about why background independence. I mean, somewhere lurking in there as well, it's sort of it's the idea of maybe somebody who's came up a bit as well, as sort of unification. In some way, dynamically, geometry shouldn't be treated differently from the other field, from other fields. Gravitons, you couldn't get. That's one, I think, a nice thing that happens in string theory. The gravitons are exactly on the same footing as any other kind of field that you can have. They're all just excitations of the string. So, I was trying to be a little provoking, but maybe we should.
I think it's not very
Sorry?
That's not probably the right one.
Well, we're a little over time anyway, so maybe we should have some coffee and then start back again. It's 11, I guess. Thank you.